All right, everyone. Hello, welcome to the second lecture of Math 162. I like to just kind of label these based on week 1, lecture 2, week 2, lecture 1, et cetera, et cetera. You obviously know the date that we're holding the class, so that's not a big deal, right? We don't have to put the date on the screen for you. We will complete 5.1 today, as well as 5.2. So that means both of those assignments will be due in 1 week by the 3rd. And remember that my due dates are always by 11:59 p.m. of the same day. I might not always write that timestamp going forward. You'll hopefully remember that going forward, but at least for the first several assignments, I will. But any tests, any homeworks, any quizzes, if we had any, they'll always be due by 11:59. Thank you for your patience for me being a couple minutes late. I believe I mentioned last class that I have a class that ends literally 1 second before this class starts, so I have absolutely no time to prep, and then Zoom is still trying to convert recordings and everything, blah, blah, blah. Class ran late today for them, and this is hopefully going to be the only time that that happens, but I'm not going to make any 100% concrete promises, but I did know in advance that that was going to happen for that class today. I had two hours of material to do. So we're going to pick up today where we left off in 5.1. Actually, before I say that, please remember that you were supposed to have enrolled in Mymathlab. I believe all of my students who had enrolled before this course started on Tuesday, I believe all of y'all got in, so that's awesome. I believe I have 2 or 3 new students who enrolled since that first class. Please know that you are 100% responsible for watching last class's lecture and understanding the dynamics of this course. I should have sent an email to you. If you have not gotten an email from me, that means that you maybe have enrolled in the past hour or something like that. I believe today is the last day to enroll, or maybe it was yesterday. I don't remember off the top of my head. My focus has been somewhere else, very obviously. But with that being said, again, we're going to pick up where we left off in 5.1. We had done some problems where we were converting between radians and degrees, and we're going to pick up by going the opposite direction from where we went. So remember that pi over 180 or 180 over pi, 180 degrees more specifically, that's our conversion, and it's just a matter of whether you multiply by pi over 180 or 180 over pi. And it is specific. And I had mentioned that if you get answers that look really goofy, like there's a pi squared somewhere in the top or the bottom, or the degree number is in the bottom, then that means you've definitely made a mistake somewhere. Generally, answers in degrees are going to be like 30 or 45 or 22.5 or 12, whereas answers in radians are going to be 5 pi, pi over 2, 2 pi over 3. They don't have to have a pi, but 99% of the time, if not more than that, they do. So radian answers tend to have pi, degree answers tend to not. So let's go ahead and pick up where we left off. I am going to have several different videos that I'm going to be pulling from today to get to the end of 5.2. And so just know that a couple times we'll have to take a 1-minute breather to set that up. And as always, if you have any questions, I will be in the chat 100% of the time. Please ask away, whether it's a private message or an entire group message.
Let's go the other way. Convert to degrees now. I'll give you a second to finish writing. And we're going to start with pi over 3. And some of you may be clever and say the answer is 60 degrees. Look at B. The answer is pi over 3, so we know it's 60 degrees. Show your work, though. Let's prove it, because it's going to be important to be able to do this later, after we've learned 50 million other things. So we take the pi over 3. Now, because I don't see a degree symbol anywhere, I know it's in radians. Also, because I see a pi, I'm pretty sure it's in radians, just without even knowing the other issue, times fraction. So this is where you go, do I multiply by pi over 180 or 180 over pi? Well, if you put the 100, I'm going to do this wrong for a second. I will erase this one. If I put the 180 degrees in the bottom, the unit's in the bottom, which means this would be per degree. And that doesn't make sense. Having degree as a unit in a bottom doesn't make sense, which is why that makes that wrong. The major clue for me, and what it probably will be for you, is out with the old. I see a pi in radians. You generally don't see that answer in degrees. So the pi is going to be in the bottom, meaning the 180 goes in the top with its degrees. 3 will go into 180 60 times. The pi's will cancel each other out. So again, 3 goes into 180 60. So that's 60. And now because I see a degree, I didn't cancel it anywhere. That's our answer. And that's confirmed earlier. 60 degrees was pi over 3, so pi over 3 better be 60 degrees. Let's do as many as we did last time. Let's go with, next up, pi over 4. So we multiply by pi over 180, right? Let's show you what this would look like if you did pi over 180. Let's actually show you. Pi times pi is pi squared. 4 times 180, well, 2 18s is 36, 2 36 is 72, so that's 720 degrees. So the answer is pi squared over 720 degrees. What in the world does that mean? My head just exploded. I had an aneurysm. So that was wrong, 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 wrong. So even when you do things wrong, if you're being monotonous and careful, meticulous and not monotonous, you might feel it's monotonous, but if you're being meticulous and careful, you can show why your answer doesn't make sense. So it's really supposed to be 180 degrees over pi. 4 will go in 180 45 times. The pi's will cancel each other out, top and bottom. We have our degrees now, so that's 45 degrees. Five pi over 3 for C. Oh, that was not what I expected to happen. You hit enter after something and it makes it go down. Word makes great sense sometimes. Am I right? So we take our 5 pi over 3. That's an ugly 5. No, not select. What's happening? What's going on? There we go. Okay. Times. And we know the rule now, 180 degrees over pi. 3 goes into 18 6 times. So that's 60. The 3 and the 180 reduces to a 60. And then you can say that 60 times 5 is 300. So this would be 300. The pi's will cancel, and you'll have your degrees in your answer. You could have multiplied first. You could say 5 times 180 is 900, and then 3 goes into 900 300 times. It's up to you. You can multiply, reduce, and whatever you like with fractions. D, 7 pi. Ooh, ugly pi. Okay, an ugly pi is still a tasty pie, right? So we multiply by 180 degrees over pi. The pi's will cancel. You'll be stuck in degrees. 7 times 18 is what, 126. So tag on the extra 0. That's 1260 degrees after the pi's cancel. You don't have to be lightning fast like that with your arithmetic, but you should be capable of doing arithmetic without a calculator. Remember, tests 1 and 2, not supposed to be using them. E, let's go with 3 pi over 2. So you multiply by 180 degrees over pi. 2 goes in 180 90 times. 90 times 3 is 270. Pi's cancel, and you're left with your degrees. 5 pi over 18. Last one. We take our 5 pi over 18. We multiply by 180 degrees over pi. 18 will go into 180 10 times. 10 times 5 is 50. The pi's cancel. So that would be 50 degrees. So that's how we go between degrees and radians or radians to degrees. Again, this is just a very, very, very minor step in the bigger picture of most of the problems that we do, if you feel the need to convert them. So some students just learn the idea of everything in degrees. If they get a problem in radians, they'll just convert it to degrees so they understand the size of it. Some people actually eventually learn a lot of the different radians and memorize them. Oh, 60 degrees is pi over 3, 30 degrees is pi over 6, 45 degrees is pi over 4. Those are very important. I would encourage you to memorize 30 is pi over 6, 60 is pi over 3, 45 is pi over 4, 90 is pi over 2, 180 is pi, 360 is 2 pi. It'd be really good to know 3 pi over 2 is 270 as well. Those are all extremely important and will be seen over and over and over and over and over. You're going to see pi over 3 all semester long. You're going to see pi over 4, pi over 2, pi over 6, 3 pi over 2 all semester long. So please take the time, make the effort to memorize those. Okay. Next topic, coterminal angles. This is something that we've already actually introduced, believe it or not, with 0 degrees being the same thing as 360 degrees, but it's not just those two that are the same. There's actually infinitely many angles that are equivalent. I'm not saying that all angles are equivalent. I'm saying that 1 degree has infinitely many other angles that are equivalent. 1 degree is the same as 361 degrees. Negative 1 degree is the same as 359 degrees, is the same as 719 degrees, is the same as 1079 degrees. I think I said that right. Because when you're talking about going around that circle, once you make a complete revolution, you're back where you started. And then if you go another 30 degrees to say 390, you're at the same location as 30 degrees. And for most of the things that we do, almost everything that we do in this course, it doesn't matter how many times you go around in a circle because you keep ending up at the same spot. So 30 degrees is the same math, the same trigonometry as what you would get if you did it with 390 degrees. Negative 45 degrees would be the same as 315 degrees. 315 would be the positive version of the angle. Negative 45 would be as if you rotated clockwise instead of counterclockwise. Draw those up really quickly. And again, I'm not always going to use these colors moving forward, but here is approximately 30 degrees. But it's also, so that's if you just go that little bit, or you could go all the way around and then to that line, I just extend it a little more for drawing's sake, that would be 390 degrees. Any of the actual trigonometry we do with 30 degrees will lead to the same answer as if we'd done it with 390 degrees. But we don't want to memorize all these different patterns for 390 and 420 and whatever, for 540 degrees, all those different ones. So when you get these big, big, big angles, we generally like to turn them into something between 0 and 360 to be able to process them. And in fact, most of the time, if we have something like 300 degrees, we're going to try and turn it into something between 0 and 90 using some tricks. But we'll get there another day. All right, initial here, terminal, we're going to go with negative 45 degrees, which would be there. So here, if you rotate this way, that's negative 45 degrees, but it's the same as if you'd gone counterclockwise instead, and that would have been positive 315 degrees. So coterminal angles have the same initial and terminal sides. And the way you can get between one coterminal angle and another is just add or subtract 360 degrees. Many times as you need to show they are the same or to find another coterminal angle. Some examples. What do we got? 15 minutes. How much is left of this? Not very, in fact, that last little bit we're not going to be covering because it was removed from the material. Perfect. sorry, back to where we were. And again, if that doesn't make sense to you, just stand up and don't move at all and think about what direction you're facing. Then do a full rotation, a full 360 degrees, a full 2 pi radians, and notice that you're looking at the same position. Nothing's really changed. Or have yourself rotate 90 degrees and then rotate another 360 degrees and you'll be facing the same position. Nothing's really changed. Spinning yourself around 360 degrees, either clockwise or counterclockwise, doesn't change anything in terms of trigonometry. All right, example 3, I believe. We are going to find a coterminal angle in the range coterminal, I can spell, I just type too fast sometimes. I can't always spell, admittedly. And I'm going to put this in degrees. Let's go 0 less than or equal to the angle less than 360 degrees. That's a terrible looking less than. Let's redo that, make it a little prettier. There we go. A, we're going to have 410 degrees. So maybe I'm asking you to do some trigonometry with this, but you haven't really studied 410 degrees very much. So it would be best to just add or subtract 360 this until you get it in the range of what you have studied more extensively. So what we can do is take the 410 to get it between 0 and 360. Well, I think it's obvious that you would need to subtract 360 degrees. And I will fix my degree symbol there. 410 minus 360 is 50 degrees. And you only had to do it once. So that's your answer. B, negative 22 degrees. So that's a negative angle, something that sometimes we like them, sometimes we don't. So let's just make it a positive angle in that, you know, kind of standard 0 to 360 degrees. Well, it's negative, so we should probably be adding 360 degrees. And negative 22 plus 360 is 338 degrees. There we go. C, 999 degrees. Well, if you just subtract 360 once, sorry, hold on, distractions. Okay, if you subtract 360 once, let's see, 990 minus 360, 936, so that's 639. That's not good enough. So what you have to do is subtract again. And if you subtract one last time, 639 minus 360 is 79 degrees. There we go. And that's in the window we want. Last one, we'll make this the trickiest, 9 pi over 2. Not even going to start out with the simple 1 in radians. We're going to do a complicated 1 in radians. All right, so 0 to 360 degrees means that we need to be between 0 and 2 pi. So this would be the same thing as saying 0. I forgot my degrees over there on the first 0. It's still technically correct because 0 degrees is 0 radians, but I want to make sure it's accurate. So this would be the angles between 0 and 2 pi radians. Notice that I had the or equals on the 0, but not on the 360. Same for this version. And that's because these two are the same. You don't want to have two representations of the same. So doing it this way is every possible angle. So we're supposed to be subtracting 360 degrees, but in terms of radians, 360 degrees is 2 pi. So we got to subtract 2 pi. Well, guess what that means? We got to get an LCD. 2 pi is the same thing as 2 pi over 1, FYI. The LCD between 1 and 2 is 2. And we will be doing this all semester long, so if you're rusty with fractions, go practice it on your own, go find your resources. Unfortunately, that's not what we're here to teach. So the 9 pi over 2 minus, that already had the LCD, so it didn't change. For the other one, the blue 1 will go into 2 twice. 2 times the 2 pi will be 4 pi. So 2 pi over 1 is the same as 4 pi over 2. If you reduce it, you get the same thing, and you can see that that's fine. All right, so 9 minus 4 is 5. Now that we have a LCD, 5 pi over 2. Is this okay or not? Well, you should be able to tell. This 4 pi over 2 is the same thing as 2 pi. This is 5 pi over 2. 5 is bigger than 4, so this is still too big. So we take our 5 pi over 2 and we subtract another 2 pi, which I'm going to go ahead and write as 4 pi over 2. There's no reason to reinvent the wheel. 5 minus 4 is 1, so that's a single pi over 2, aka 90 degrees. So here's the thing. If you hated that, what you can do instead, and I don't care if you do it this way, but you have to know one of the two ways, you could have converted the 9 pi over 2 to degrees by multiplying by 180 degrees over pi. Then you would have whatever it is in degrees, I don't know off the top of my head, doesn't matter, and then you just subtract 360 degrees, and then you subtract 360 degrees again, and you'd end up with 90 degrees there. 720, so that means this was 810 degrees, not that it ultimately matters. So if you convert this to degrees, you should get 810, subtract 360, then 360 again, and you'd get 90. But here's the thing. If Mymathlab gives you a homework or test problem in degrees, it probably wants the answer in degrees. If it gives you a homework or a test problem in radians, it probably wants the answer in radians. So if you wrote 90 degrees for this, most of the time, Mymathlab is probably going to mark it wrong, and you're going to be mad at yourself because you didn't do that last conversion process. So that's why I say you can do that, but I didn't write it down because it's a longer method and it leaves more wiggle room for mistakes that we don't want you to make. All right, a couple last minute features. First of all, I'm actually going to point out this. To find complementary and supplementary angles of something, two complementary angles add to 90. So if you know one, you're going to do 90 minus it to find the other. For supplementary angles, they add to 180 degrees. If you have a hard time remembering that, they're in alphanumeric order. 90 comes before 180, C comes before S. Smaller number, smaller letter, larger number, larger letter. So if two angles add to 180, that means if you know one, you can find the other by doing 180 minus the first. If two angles are complementary, aka they form a right angle, that means they add to 90 degrees. So I'm going to draw those as a picture. So here, that's weird. Why did that happen? Okay. So here is angle 1. I'm going to do a little 1 to denote they're different. And then here is angle 2. These would be complementary angles because they add to 90. So if I knew the first one was 30, I could do 90 minus 30 to get the other one being 60. And certainly 30 plus 60 is 90. Supplementary angles add to 180 degrees, which means they form a straight line. So maybe your first angle is here. On the right side, that's angle 1, and then here's angle 2. Since they form a straight line combined, that means they are supplementary. So let's say this bigger angle was 140 degrees. You do 180 minus 140, and that would tell you that this other angle has to be 40. And you could prove that because 40 plus 140 is 180. So those are pretty easy problems that will come up throughout the semester. We will need the complement and supplement of angles sometimes, and we'll get into the why and when then. Something that honestly we will not be studying in the rest of this course, I'm trying to highlight this without the drawings, but okay, you get the idea. Just pretend like I'm highlighting these two lines. This is an important concept, especially if you were going to go on to say physics, because it's the relationship between an angle, the arc length, and the radius. And it has everything to do with radians. When we said 1 radian was where its arc length was the same as its radius, and then the angle would be 1. So if these two things were the same, S and R, if the arc length and the radius were the same, then the angle would be 1 radian. If the arc length was twice the radius, that ratio would be 2, and it would be 2 radians. So using this formula, if you will, that an angle is the ratio of its arc length to its radius, that's the true idea of how we understand an angle in terms of radians. You can't do that in degrees. This process, this formula does not work in degrees. That's why we call it radian measure. So again, in the true basic definition sense of what an angle is, in radians, it's the ratio of arc length, which is that curvy distance along however much of the circle you're doing, to its radius. If you multiplied both sides by r, then you'd get this equation instead, that an arc length is the product of its radius and its angle, but only in radians. So this is what I was mentioning, that some things don't work in degrees. If you want to talk about arc length at all, you can't use degrees. You absolutely cannot use degrees.
All right, so just give us a second while we get to the next vid. All right, so that concluded 5.1. So again, that homework will be due in a week, and we're about to start 5.2, and we will be able to finish it today just in time. So go ahead and get ready for the next section. And as you're about to hear me say, this is one of the more important sections. This is one of the many bricks in the foundation of trigonometry. This is stuff that we'll be using over and over and over and over and over all semester. Let me know if the audio's messed up. Sometimes when I change videos, that happens.
Things. Today is a very important lecture. If I were going to say that any day's lecture was more important than any others, this would be the one. This is the lecture that if you don't learn it, you can't do anything for the rest of the semester pretty much, because we are going to talk about the 6 primary functions of trigonometry, kind of what they are in relationship to a right triangle. And we're going to go through and study some numbers involving them, some examples, and et cetera, et cetera, et cetera. But we need to start out with just straight up definitions. So what does a right triangle look like as a reminder? Right triangle is one in which there's a 90-degree angle. It's not perfect, but again, it's kind of hard to draw on this tablet, so I do my best. So there's a right triangle. Now, we're using the Greek letter theta. Looks like a 0 with a little curly line through it. Sometimes you'll see me draw it a little straighter than others. It doesn't matter, as long as it's got something to show that it's not 0. So that is theta. That's our angle. So this right here, for now, is the angle we're interested in. And in relation to that angle, these 3 sides can be given names. This vertical length over here on the right, we can call the opposite side. This horizontal length on the bottom, we can call the adjacent side. And these names are, what's the word I'm looking for? Relevant, because adjacent means the side touching the angle we're interested in. Opposite, this is the side opposite to the angle. So here's your angle, here's the opposite side. So again, the adjacent is the side that touches it, but not this one. You might say, well, isn't this adjacent too? Well, yes, it is technically adjacent as well, but we don't call it adjacent. We call it the hypotenuse. So the slanted side in this position, specifically the one opposite the 90-degree angle. So when you're dealing with a right triangle, the side that is opposite the right angle is what we call the hypotenuse. So opposite, adjacent, and hypotenuse. And you'll see me abbreviate these OPP, ADJ, HYP quite often. Sometimes I'll go single letter O, A, and H. And that's all fine for me as well as for you for note-taking. In my math lab, if they want you to spell out the word, make sure that you're spelling out the word. So we are going to study the 6, yes, count them 6, trig functions. They all relate to those those 3 over there, the opposites, adjacents, and hypotenuses. Can't hit enter, but I can hit tab. There we go. So the first one is sine, S-I-N-E, but we usually abbreviate it as S-I-N. The next one is cosine, which we usually abbreviate as cos. I'm going to tab these so they're a little prettier. Then the next one after that is tangent. Like me, I like to go off on a tangent. Not the same type of tangent, but touch and go kind of idea. That abbreviation is tan. After that, why is that tab so much further than this one? That doesn't make sense. Okay, whatever, doesn't matter. Those 3 are the ones that we're going to use more than the rest. But the other 3 are important and will be used quite frequently. Don't think you can just skip learning these completely. We have our cosecant, which the abbreviation for that is CSC. We have our secant, which its abbreviation is SEC. And then we have our cotangent, which its abbreviation is COT, C-O-T. So those are our 6 trig functions that will be used every day of this course until we get out of trigonometry for things at the end of the semester. And they all are related to the opposite, hypotenuse, and adjacent. In fact, these are all heavily related to each other. A cosecant is related to a sine. A secant is related to a cosine. A tangent is related to sine and cosine. In fact, you can relate cosine and sine. You can relate any of these 2 together in some way, shape, or form. How are these defined, though? What exactly tells us what the sine is? So a sine tells us to do something with 2 of these 3 things. A cosine tells us to do something with 2 of these 3 things. Every single one of these 6 functions deals with 2 of these 3. So each of these trig functions deals with 2 of the 3 sides. So it might deal with the opposite and hypotenuse. It might deal with the adjacent and the hypotenuse. It might deal with the opposite and the adjacent. How do they deal with them? They're all fractions. They're all ratios of one to another. So those trig functions are just a measure of the ratio of an opposite to a hypotenuse, or an opposite to an adjacent, or an adjacent to a hypotenuse, whatever combinations you can think of, and it's all 6 combinations. So specifically, sine of theta, and I'm going to use my pen now. So we don't just write SIN, we have to put the angle in there. So it'll be SIN, and then there would be a theta next to it. And I want to do this in black, not red. Pardon me there. So the sine of theta. So again, sine is talking about the trig function itself. It tells us what ratio we're going to do, and then of the angle theta. So that tells us this one. There could be another angle up here. We could label this alpha or gamma or whatever other Greek letter we like, which we'll get into later in the semester. But again, we're interested in that ratio from this angle, not this angle, because if we're up here, that changes what we would label as opposite and adjacent. These 2 would actually swap. So sine is the ratio of specifically opposite to hypotenuse. And I'm going to use the 3-letter abbreviations. Opposite over hypotenuse. Give myself a little more room. Cosine of the angle is the ratio of the adjacent to the hypotenuse. And then tangent of the angle is the ratio of the opposite to adjacent. Those are the 3 most important trigonometric relations we will study all semester because they are the first brick in the building. They are a building block. They are essential. Without that, you can't do anything else. And these are the 3 of the 6 that we use more often than the others. And I'll go ahead and say why. Because each of these 3 is just the reciprocal of the one it is to the right of. So sine and cosecant, you can find one if you know the other just by flipping it. The same relationship holds between cosine and secant. The same relationship holds between tangent and cotangent. So if sine is the opposite over hypotenuse, that makes the cosecant of the angle the hypotenuse over the opposite. If cosine is the adjacent over the hypotenuse, then secant of the angle is the hypotenuse over the adjacent. And if tangent's opposite over adjacent, that makes cotangent or cot of the angle adjacent over the opposite. So again, please note that each one on the right is just the flipping of the one on the left, flipping be reciprocal. Now you'll need to know how they relate. You can't just write sine next to tangent and say tangent's flipping sine. No, that's not the case. It's cosecant is flipping sine. Secant is flipping cosine. Cotangent is flipping tangent. And a lot of people, sorry, I'm coughing, give me a second. A lot of people will think that sine and secant are reciprocals of each other and cosine and cosecant are reciprocals of each other because the s's and the c's. Well, what I would suggest is to actually pay attention to the last one because that one tells the tale. Tangent, cotangent. So the one that is a co of something is the flip. So cosecant is the flip of sine. So sine doesn't have the co, but cosecant does. Cosine has a co, but secant does not. So those are the 2 flips of each other. Again, one has a co, the other does not. And then tangent and cotangent, one has the co and the other does not. That is the, in my opinion, easiest way to remember which one is a flip of the other. Secant and sine, those words are kind of related to each other. So this is, but you can't say cosine because that's something completely different. And there's a strong relationship between all of these words. But sine, cosine, secant. And don't think that these 2 flip each other because of that. That's one thing that you could go wrong on. Sine, secant, cosine, secant. Sine, cosecant, cosine, secant. One of these has a secant, one of them has a sine. Tangent and cotangent, both of them still have tangent in them. It's just one has the co, the other does not. Now there is a wonderful abbreviation Sohcahtoa. This is helpful in the same way that FOIL is helpful for a lot of students, in the same way that PEMDAS is helpful for a lot of students. It's a mnemonic device to help you remember the left 3. So I'm going to put a little divider between here, between the left 3 and the right 3. This Sohcahtoa is helpful for the left 3, for sine, cosine, and tangent, because as I said, these are the ones we'll deal with way more often. We'll see them way more often, and most of the time, when we see these other 3, we end up just either in our heads or on our pages, turning them into the others to actually understand them. So Sohcahtoa. This will help us remember the sides and in relation, sine, cosine, tangent. Sine, let me use the abbreviations, is the opposite over hypotenuse. Cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. Let me just do it this way. That's Sohcahtoa. S-O-A-C-A-H-T-O-A, and I uppercased all the appropriate letters. So that's so, S-O-H, C-A-H, Toa. Some people like a mnemonic device, kind of like, please excuse my dear Aunt Sally, and what they can do with this is some old horse caught another horse taking oats away. There's another one that I really like to use in a non-recorded class. It's got a little bit more humor to it, and I'm just always a little apprehensive to record things with certain words or phrases, and it's not a cuss word or anything like that, but I just don't want to have in a recorded lecture, and I really dislike that, but it's 2020. I don't want to lose my job over something as ridiculous as a funner version of this. So that's the one you're going to get. If we had me in person, there'd be another one, because then nobody could prove I said it right. Haha. And even that's probably, that's definitely not true, but I just felt more okay with it. So maybe go to the internet and just look up more fun phrases that can go with Sohcahtoa, and it's probably easy to find, as well as maybe one or two others. But that's the one you're going to get from me, whether I like it or not. Some old horse caught another horse taking oats away. I'll even give you some hints as to what it was. Instead of horse, it was hippie. And instead of taking, it was tripping. And I'm sure he or she was not just falling over, but again, I didn't say anything besides that. Some old horse caught another horse taking oats away. Sohcahtoa. I think Sohcahtoa, as long as you know the letters of them, you're not thinking it's S-O-C-A-T-O-A. As long as you know it's 3 letters for each one, I think that that's perfectly fine. So, S-O-H, that says that sine is the opposite over the adjacent. Oops, I don't want blue, I want black. So if here's our angle, and we wanted to know that the sine of theta, it would be its opposite over the hypotenuse. It would be its opposite over its hypotenuse. That's how we can use that. Or if we wanted the cosine of theta, I'm only labeling the ones that are relevant this time. If we wanted the cosine of theta, and again, these have to be right angles here. Well, cosine is the adjacent over the hypotenuse. It's a terrible looking J, but it's a J. So adjacent is the, not that one. I'm sorry, I'm looking at the wrong thing. ADJ over the hypotenuse. So it would be this number over that number. You'd have numbers there. And then if you wanted tangent, that uses the opposite and adjacent. You're just looking for 2 numbers on a triangle and dividing them in a specific order. That's it. You need to embed this in your brain. You do not get to forget this ever this semester. If this was an in-person class, I could just randomly quiz 1 or 10 students on this and say, Sohcahtoa, what's cosine? And they should know it instantly. In fact, for my in-person classes, I usually give a quiz on this the next day after we teach it. I'm not going to do that with the scenario we're in right now, but just note that it's equally as important. You need to pretend that we have a quiz on this Wednesday and have this memorized by then, because remember, when we go on to 1.5, you probably need to know 1.4 to understand it. This is the first building block of really doing trigonometry. Yeah, we learned how to convert between radians and degrees last time, but that's not really a trig problem that I'm going to be testing on, as I've mentioned. That's just part of, hey, if I give you something in radians and it's not understandable to you because you like degrees, then you can convert it to degrees. Sohcahtoa, Sohcahtoa, Sohcahtoa. Let's try it out. Example 1. Evaluate the 6 trig functions given the following triangle. A, and I'm going to put our angle right here. I don't have to do the angle here. We will very often put the angle up here. You'll have a homework problem where the angle's up here, and you have to remember that the opposite and the adjacent, the opposite would now be the bottom and the adjacent would be this vertical side instead. So we're always thinking opposite in terms of the angle we're considering. And the sides lengths are going to be 3, 4, and 5. This is a very cool right triangle because all 3 of these are integers or whole numbers. You don't get that very often in right triangles. There's only a couple of right triangles as a basis where that's true. Most of them have a radical somewhere in at least one spot, as we will see moving forward. All right, so we're going to do the sine of theta. We're going to do the cosine of theta. We're going to do the tangent of theta. Then we're going to do the cosecant of theta, secant of theta, and the cotangent of theta. Now again, all we're doing here, we have these sides labeled. First of all, moving forward, you generally don't get all 3 sides labeled. Only 2 will be labeled, and you'll have to find the 3rd side using something known as the Pythagorean Theorem, which you've probably heard of, you've probably used, but we'll remind you of soon. So all I'm looking to make is a fraction involving 2 of these 3 numbers. That's all these trig functions are as a basis. It's a ratio of one side's length to another side's length. But that ratio gives us a whole bunch of things that we can use moving forward. All right, so sine. So, S-O-H, S-O-H, so in Sohcahtoa. Opposite over hypotenuse. So in terms of this triangle with our angle here, that makes the opposite the 4 and the hypotenuse the 5. See, if our angle was up here, the opposite would be 3, because then that would be opposite. So opposite is 4. The hypotenuse is always the side opposite the 90-degree angle. So that's the 5. So our answer is 4/5. That's it. That's the entire 1/6 of the problem. Nothing crazy. The cosine of this angle, so that's ca, C-A-H. Cosine is adjacent over hypotenuse. Adjacent meaning the side that it touches, not the hypotenuse, and then hypotenuse is the opposite of the 90 angle. So 3 is our adjacent, 5 is our hypotenuse, and you got to get the order right. It's not 5 over 3, it's 3 over 5. Tangent, TOA. Now again, you don't get an abbreviation for cosecant, secant, and cotangent. Nobody's really come up with a clever mnemonic device for it. And plus, with the whole reciprocal relationship that I will actually write down formally later, it's just really easy to find these 3 based on the other 3, but we'll get there. Tangent is TOA, opposite over adjacent. So again, here's our angle. Opposite was 4, adjacent was 3. There's nothing insane about this. It's just understanding which one you label opposite, which one you label adjacent, and memorizing a few little details. So opposite 4, adjacent 3. So there are our first 3, 4/5, 3/5, and 4/3. Cosecant, secant, and cotangent. These are, again, the basic idea is the reciprocal of these, but let's actually go to the standard definitions for now. Cosecant is the hypotenuse over the opposite. Maybe for these first couple, you even want to label these. Maybe you want to label the 3 as the adjacent. Maybe you want to label the 4 as the opposite. Maybe you want to label the 5 as the hypotenuse. You're more than welcome to do that. So we want cosecant, which we said was hypotenuse over opposite. CHO, it's show, maybe, I guess. CHO, like using the C with an S sound. Show, SHA, show, sha, cow, CAO. I mean, I can't even, every semester I try and get to that without laughing, but I gotta laugh. Show, sha, cow. Okay, so cosecant. That's the hypotenuse over the opposite. Hypotenuse over opposite, 5/4. And I'm doing these in red for a reason. Secant. If you go back up here, secant was the hypotenuse over the adjacent. Hypotenuse over adjacent, the sha. Hypotenuse was still the 5, the adjacent is still a 3, so that's 5/3. And then cotangent, if you go back up, is adjacent over opposite. Adjacent over opposite. Adjacent's 3, opposite's 4. 3/4. That's it. That's the entirety of example 1A. Notice the reds are the blues, but flipped. 4/5 flipped is 5/4. 3/5 flipped is 5/3. 4/3 flipped is 3/4. Now, there's, again, an association here. I can't just put the cotangent next to the sine and say that that's the flip of that. 4/5 is not flipping 3/4. It's these two are directly linked together in terms of a flipping. These two are linked in terms of a flipping, and these two are linked in terms of a flipping. If you write them in a wrong order and try and use the flipping in that manner, you're going to make mistakes. And again, that's something that I will label after one more example. Yes, one more example. B. I want it in black. Back in black. All right, so this triangle, and I will admit, the 3, 4, 5 triangle, while it's awesome that they're all whole numbers, we really aren't going to use this triangle too often in this class. In that admission, I will also admit this triangle, which has opposites and adjacents no matter where you are, being 1 and 1, so they're the same length, has a hypotenuse that is the square root of 2. I will at some point actually prove that this is the case. And we're going to keep our angle here, but because the opposite and the adjacent are identical, you could actually put the angle here and it would not change anything. Kind of cool, if you ask me. But my definition of cool is, well, weird sometimes. So again, let's find the sine of the angle, the cosine of the angle, the tangent of the angle. Notice I don't get to skip writing this. If I just write CSC, SEC, and COT equals, this is bad form because what's the variable? What's the angle? What's the x? Remember, theta is basically our x for trigonometry in a lot of cases. So which angle do you mean? Do you mean this angle or do you mean this one? Or do you maybe mean the right angle? Because you could still somehow at some point talk about sines, cosines, tangents, cosecants, secants, and etc. from a right angle position instead. We're not there today though. Okay, so theta, theta, theta. Sometimes my thetas look like 2s. Please forgive me. I was not graced with amazing handwriting. I'm left-handed, so There you go. There's my problem. All right, blue for the first three. Sohcahtoa. Sohcahtoa, S-O-A. Remember, you can label them if you like to. I'm going to try and avoid it this time, though. It's pretty much labeled above, though. This one is the opposite. This one is the adjacent. So, S-O-H, opposite over hypotenuse. The opposite is the 1 over the hypotenuse's square root of 2. I did not leave myself enough room here. I just need to move these to the right a little bit. You know what? That's not going to work. I'm just going to start fresh. I just want to rewrite those a little further to the right because I need to simplify that 1 over square root of 2 in a second. So this is cosecant. This should be enough room. And then cotangent. So 1 over square root of 2, because this was the 1 and this was the square root of 2. Opposite over hypotenuse. This right here is a terrible format for an answer. Terrible format for an answer. You never, in this course, unless it's an extreme situation and I mention it, you can never leave an answer as 1 over square root of 2. It's this that's the issue. You can't have square roots in the bottom. You should have learned that in pre-calc. You should have learned that before pre-calc. You should have learned that in like an Algebra 2 class, in fact. So you have to do what's called rationalize the denominator. And I'm going to make a memo about this after the example is done, but you have to do what's called rationalize the denominator. What we do is we multiply top and bottom by what the bottom is for this case, because there's no pluses or minuses. This is an easier case. You're just going to multiply top and bottom by the square root of 2. So if your bottom is square root of 2, square root of 5, square root of 13, this is the technique. Multiply top and bottom by the square root that's in the bottom. And what that's going to do for us, oh, my blue back. The top, 1 times square root of 2 is a square root of 2. In the bottom, square root of 2 times square root of 2, since they're both inside, makes the square root of 4. But we know what the square root of 4 is. It's 2. So the answer is the square root of 2 over 2. Room. So this right here is called rationalizing a denominator. When you have a monomial, just one term in the bottom, a square root of 2, square root of 5, and we will see this literally hundreds of times in this course. So if this is rusty, derust. Multiply top and bottom by the square root that's in the bottom, and that will get rid of the square root because we cannot have square roots in denominators of answers. It's okay in the top, but not the bottom. And it's funny because this answer looks uglier than the original problem. And yes, it does look uglier, but there are things we can do in this format that we couldn't do or recognize in the original format. So this is very important, and it might look silly. You might think it looks worse, but again, in terms of math, it is better, it is simpler, it is more functional. So let's try out the cosine. 1 over square root of 2 was the sine initially, because that was the opposite and that was the hypotenuse. Well, cosine is ca, C-A-H, adjacent over hypotenuse. Adjacent's the one that touches the angle, so this is the adjacent. It's still a 1, but it's the different one. So that's 1 over. Hypotenuse, still square root of 2. Again, these ones at the top are different. The sine one was this one, whereas the cosine's one was this one. It's just coincidence. But also coincidence, we can't have a square root in the bottom, so we gotta multiply top and bottom by square root of 2. And that'll give us the same thing, ultimately giving us square root of 2 over 4. Same middleman work, I'm not gonna reinvent the wheel. For the tangent, TOA, T-O-A. Let me write that one last time. S-O-H-C-A-H-T-O-A. You'll see me write that in class for the next month or two, probably. So TOA, T-O-A, opposite over adjacent. This is the opposite one. This is the adjacent one. So it goes 1 over 1, which 1 divided by 1 is 1. Much simpler, that one. Okay, well, what about these other three? I didn't leave as much room for them, interestingly enough. Do you think maybe I've got to do this again? Maybe not, maybe not, maybe not. Let's see what happens. So let's make my orange red again. So cosecant, remember, this is going to be hypotenuse over opposite. And if you are rusty, not rusty, if you haven't learned that yet, go back to where you read it. You wrote it. Read it 50 times, write it 50 times, use it 50 times, whatever you have to do to learn this stuff. Cosecant is hypotenuse over opposite. Hypotenuse was the square root of 2. The opposite is this one right here. So square root of 2 over 1. But we can have square roots in the top. But 1 in the bottom means we don't need the bottom. So that's just square root of 2. Now you might say, well, Mr. Beckner, that doesn't look like you took the previous one and flipped its answer. You kept saying that. Well, actually, if you flip the initial thing before you did all this cleaning up for its particular problem, if you flipped 1 over square root of 2, you'd get square root of 2 over 1, which is square root of 2. If you flipped this version, the answer, you would have to go through and do this orange step again. And believe it or not, by the end of it, you would get the same answer, but I'm not going to do it that way. Secant. So cosecant was the hypotenuse over the opposite. Secant is the hypotenuse over the adjacent. Hypotenuse over adjacent. The hypotenuse being the square root of 2. The adjacent being this one. Still a 1, but it's the bottom one. And square root of 2 over 1 is once again square root of 2. Time I say once again today, I got Bernie Sanders in my head. Once again, I am asking you to do trigonometry. Cotangent. So TOA that was opposite over adjacent. Cotangent's adjacent over opposite. Adjacent 1, opposite 1. That 1 over 1 is still a 1. I will put less of an emphasis on these later 3 trig functions versus the first 3 in the memorization of opposites, hypotenuses, and adjacents. I will even be completely honest with you. I don't have them memorized in my brain that way. You know why I don't have them memorized in my brain that way? Because I know that cosecant and sine, I can get the sine and flip it. That's easier than memorizing a whole new set of opposites, hypotenuses, and adjacents, especially if they don't have a helpful mnemonic device like Sohcahtoa. So again, you can certainly do them this way. You can do them that way all semester. As I said, myself, and I emphasize that learning can be done from multiple angles, from multiple methods. I'm not the math teacher that says, do it my way or you get an F. Never have, never will. I'm the teacher that says, if you have a method that always works, use that method. Who cares how you get the job done? As long as it's legal. Okay. So, what are those relationships, those reciprocal relationships? There we go. It always takes me 1 or 2 times to spell that correctly. Reciprocal relationships. It's that cosecant.
I'm actually pausing for just 1 second. I didn't even realize I had that. Square root of 2 times square root of 2 is square root of 4, which is 2. I just caught that. Thank you for catching that in the chat. So I have that corrected on the screen just for a second. So please, please, please make sure that you have that accurate in your notes, because the second I scroll the screen, that scribbling is going to change. Just going to hold it for 5 more seconds and then we'll pick back up.
Of an angle is 1 over sine of the angle. It is that secant of an angle is 1 over cosine of an angle, of the same angle, of course. And that cotangent is 1 over tangent of the same angle. These are the reciprocal relationships. Saying 1 over means flip it. You don't have to do it as a 1 over. If it's originally a fraction, then you just flip the fraction. I hope everyone knows what a reciprocal is at this level. Flip the fraction, or take 1 over it if it was a whole number. Then what we also have are our relationships between tangent and cotangent versus sine and cosine. I don't want to use a slash for that. Tan and or cotan relationships, relations to sine and or cosine. So tangent of theta is the sine of theta over the cosine of theta. I haven't said that one yet, but it's true, and I will show you why. The cotangent of theta, if you understand the idea of reciprocals, if tangent is this, cotangent is a reciprocal of tangent, then just flip the sine and cosine. It should be cosine of theta over sine of theta. Now, this is not a very heavy-handed proofs class, but I will prove some things. I will prove some things. I will prove the tangent relationship. So let's take the tangent of theta is supposed to be sine of theta over cosine of theta. But here, on this step, let's replace with opposites, adjacents, and hypotenuses. So at this step, so after the equals, you will no longer see the word sine and cosine, you'll see words like opposites, adjacents, and hypotenuses. Hypotenuse, the plural of hypotenuse. Not that anyone cares. So sine of theta, that was so, S-O-H. Sine is opposite over hypotenuse. So the sine of theta is opposite over hypotenuse. So the top fraction, the top of this fraction is going to be a new fraction. It's the opposite over the hypotenuse. And in fact, let me do the bottom in orange. Oops, that's not what I wanted. Let's do cosine of theta. Drop. Thank you. There we go. Colors are always helpful for proofs. So sine, the red, was opposite over hypotenuse. So there's the top of the fraction. Here's the black division. Here's the black division. Now the cosine of theta, that's ca, C-A-H. Cosine is adjacent over hypotenuse. So A, D, J over H, Y, P. Now, this is a fraction divided by a fraction. This is not the only time this semester that you'll see this. This should not be the first time you have ever seen this. You should have been taught how to handle fractions on top of other fractions, also known as a compound or complex fraction, depending on your teacher and textbook that you've used. As long as there's no pluses or minuses mixed up in this, like another fraction is being added in the top or subtracted in the bottom, you can just turn this black fraction bar into the old school division bar. So with red, let's put red here. So the red, the opposite over the hypotenuse. And instead of the black ink being a division bar as a fraction, let's make it the division symbol. And then we have our orange ink, adjacent divided by hypotenuse. The only thing I've changed was I turned this right here into this. Fractions are divisions. But how do we divide fractions? We multiply by reciprocals. So we don't change the red. The first one does not change. And if this is something that you don't remember or are rusty with, guess what I'm going to say? You got to practice, 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 because I already said it's going to be seen all semester long. With the orange, we flip hypotenuse over adjacent. And then what we can do here is cancel. There's a hypotenuse in the bottom. There's a hypotenuse in the top. So we can cancel those. And for the interest of my future notes, I'm just going to rewrite it. So equals down here OPP over HYP times HYP over ADJ. The hypotenuse, the hypotenuses, whatever you want to say, they cancel. So we end up with opposite over adjacent. So after simplifying this, we get down to opposite over adjacent. Opposite over adjacent, why does that sound familiar? Go back to your definitions. Opposite over adjacent, which one of these is it? Opposite over adjacent, right here. Tangent is the opposite over adjacent. So this is equal to tangent of theta. That is the same thing as this, so that is a proof. You will see a fancy abbreviation from me sometimes for proofs, QED. It's Latin, quod erat demonstratum, and I'm not going to spell that out because I'd have to look it up first. Quod erat demonstratum. It means quite literally that which was to be demonstrated has been. It means proofed. It means done. So a lot of people like to say QED when they're done with proofs because they feel like it makes them sound fancier, and it makes them sound like, well, even if I got a mistake in here, since I said QED, the teacher's going to think I did it right. Trust me, I know better. Most of your math teachers know better. I said most, not all. Exceptions to every rule, right? All right, how are we on time? Halfway there, halfway there. Okay. So the proof of the cotangent relationship is quite literally the exact same as here, except the orange and the reds are all upside down from each other. The orange would be before the red here. The hypotenuse would still cancel, and you'd end up with orange over red here, which would be the cotangent. It would have been adjacent over opposite. You can see similar proofs done for these three relationships as well, but I think it's pretty easy just to see based on appearances. If you look at sine, if you flip these two things, you get cosecant. So that proves, good enough, right? That cosecant is flip sine. The same relationship holds between secant and cosine, the same between cotangent and tangent. You don't have to write the left version as the left and the right as the right. I can write that sine is equal to 1 over cosecant. I can write that cosine is equal to 1 over secant. I can write that tangent is equal to 1 over cotangent. All of those are perfectly fine because they're reciprocals of each other no matter what the format is. It's like two sides of a coin. If you flip a coin once and then flip it again, you're back at the original. So you can say heads is flipping tails, or you can say tails is flipping heads. And when I say flip, I mean once, not to flip it with your thumb in the air many times. I mean literally to just change from one side to the other. A looser definition of flip, if you will. And then I won't say last important theorem, but the last one from this section for now, to go with these, is the Pythagorean Theorem. I mean, this is just all over the media, not just in your actual math class. It's if you've got a right triangle, no matter how you draw your right triangle, this is just the classic way I like to do it. The things that we've been calling opposite and adjacent, so this would be opposite and the bottom would be the adjacent, those are known as legs. So legs are attached to the right angle. The hypotenuse is not a leg. So you'll hear me, not see me, because you don't see me literally, but you'll hear me say that phrase semi-frequently throughout the semester. Instead of calling these hypotenuse, opposite, and adjacent, let's give them letters because that's how the Pythagorean theorem is done. Let's call the legs A and B. These are completely interchangeable. I can swap A and B. It doesn't matter because the Pythagorean theorem doesn't actually have anything to do with this angle theta. And then the hypotenuse we traditionally call C. And the Pythagorean theorem states that the sum of the squares of the legs is equal to the square of the hypotenuse, the side opposite the right angle. And you'll see movies and TV that like to say that a lot fancier and more wordy, I suppose. But it's just a squared plus b squared equals c squared. We're not going to prove this. There are tons of proofs. My favorite always being the geometric version, where you actually draw out a square of length A on the bottom, a square of length B to the right of it, and then a square at an angle of length C. And basically you geometrically rearrange the shapes so that the two squares below and to the right end up fitting in the square where C is. If you don't memorize this theorem, you're going to have as much of a difficult time throughout this course if you don't memorize Sohcahtoa and the actual relationship between sine, opposites, adjacents, hypotenuse, cosines, tangents, all that stuff. We will use this constantly throughout the semester because I traditionally do not give you all three sides of a triangle. Going back to these two previous examples, I normally wouldn't have given you maybe the 5 here or maybe the 1 here. Or maybe I don't give you the 4 and I give you the 3 and the 5. Because we can always use this and its algebraic rearrangements to find the other side. So some variations to this. And I'm not asking you to memorize these, but it would be that C is equal to the square root of A squared plus B squared. Or you could say that A is equal to the square root of C squared minus B squared, or that B is the square root of C squared minus A squared. This is just an algebraic rearrangement of those three things and solving for the other. Now you might say, all right, well, you took a square root. Why didn't you do a plus or minus square root? Because usually when you take square roots, you plus or minus them in an algebra sense. Notice I said in an algebra sense. These always relate to geometry. We can't have negative lengths in geometry. So how could A be a negative square root of something? That would make it negative, which doesn't make sense. That's why we don't worry about the plus or minus square roots here. In fact, a lot of the time in this course, that super important plus or minus aspect from pre-calc 1 won't be an issue in here. I'm not saying it's never an issue. I said usually. Now, if you're going on to calculus, that issue will come back so you don't get to forget it. That's the thing about math. Most of the things you learn, you usually end up reusing in a later course. I did say most, I did not say all. So with that in mind, let's try out example 2. Find the missing side. And we'll have a right triangle with our angle being here like I prefer generally. And we're going to have sides of 1 and square root of 3. So we'll call this C since it's the unknown and it's on the hypotenuse. Now, I did not ask for the 6 trig functions this time. I just asked for the missing side. This is just to demonstrate Pythagorean. So the a squared plus b squared equals c squared. The a would be, you could call the 1 or the square root of 3, just as long as the b is the other one. So if you want to label those, let me make this blue again. You'd say, I'm going to choose to say a is 1 and b is the square root of 3. So using that formula, and again, I'm going to always start with the black one. Some students will memorize these rearrangements, but me personally, I just always do the rearrangement as I go. So plugging those two in that equation, c is unknown. So we get, we'll get 1 squared plus the square root of 3 squared equals c squared. A squared plus b squared equals c squared. 1 squared is 1. Square roots and squares in this form cancel as long as there's no pluses or minuses inside without parentheses. So that's a 3. And then that's c squared. 1 plus 3 is 4, so we get 4 is equal to c squared. Then you need to take not a plus or minus square root, just a square root. No plus or minus is necessary, again, because this is geometry. You can't have negative distances. You can have negative angles, but not negative distances. So the square root of 4 equals the square root of c squared. The reason we did that is because square roots and squares cancel. And we get 2 is equal to c, and that's our answer. This is one of the 2 most common triangles we will study throughout this course. This is known as the 1, 2 square root of 3 triangle, also known as the 30, 60, 90 triangle, as we'll come to see in passing sooner than later. The other one that we primarily use is this 1, 1 square root of 2 triangle, also known as the 45, 45, 90 triangle, as we'll come to see in passing. So that's how we can find a missing hypotenuse. If I give you the legs, again, the A and the B won't matter because they would just swap the position of the 1 and the 3 here. The order of addition doesn't actually matter. B, let's draw it to the right instead, just to change up one tiny little thing. Here's our angle, not that the angle will matter. I'm going to choose to label this as A, then this will be 6, and then this will be 9. So this is an A, whoops, that was weird. This is an A on the left, this is a 9 on the hypotenuse. If you wanted to call this a B, nobody's going to care ultimately, but I chose to call it an A. So the A is A. That makes the B 6 and the C 9. So plugging those into Pythagorean, which was right here. A squared plus B squared equals C squared. So we go A squared, because A is A, plus B squared, which is 6 squared, not plus, equals 9 squared. 6 squared is 36, 9 squared is 81. You better be able to do that without a calculator. And this is just an algebraic equation to solve. So we subtract 36 on both sides. Like I said, I'm not actually using these variations. That's just ultimately what it ends up boiling down to. So we get A squared is equal to 81 minus 36, which is, what's that, 45? Then we take the square root. So the square root of A squared equals the square root of 45. I'm going to need some more room, so let me just go over here from there. The square root of A squared is A. The square root of 45 we do not know, but we will not stop here, because 45 can be broken up. Remember, in pre-calc and in Algebra 2, you should have learned that if you can simplify these, you have to. Even though I can't take the square root of 45, I can write 45 as a product of two numbers, and the goal is so that one of these numbers you know the square root of. Specifically 9, I know the square root of, so 9 times 5. You might say, well, why not do 3 times 15? Because I don't know the square root of 3 and I don't know the square root of 15, so it doesn't help. The square root of 9 you can pop out. It's 3, so we get 3 square root of 5, and that's as far as we can take it. I know it looks more complicated than square root of 45, but same thing as I mentioned earlier with the radicals and bottoms. This is technically a simpler answer, and we can do things with 3 square root of 5 that we can't do with square root of 45. Not in regard to this problem, but in the bigger picture. There we go, time, 18 minutes. Cool. So that's how we can find a missing side, whether it's the hypotenuse or it's one of the two legs. And it never matters which the two legs you're looking for, and it never matters what variable you call the other one. I could have called them x in both instances, but I just tend to call hypotenuse C and a leg either A or B personally. All right. So we mentioned the Pythagorean theorem was a squared plus b squared equals c squared. From the Pythagorean theorem, we can get 3 Pythagorean identities. So this is from, and again, the Pythagorean theorem, I'll put above it, was the a squared plus b squared equals c squared. Now, if you instead of writing a, b, and c, if you wrote opposites, adjacents, and hypotenuses where they were appropriately supposed to be, then you can play around with this thing by dividing a bunch of stuff, and you end up getting these 3 things that I'm about to show you. You get that sine squared of theta plus cosine squared of theta is equal to 1. So that's the first Pythagorean identity. We get that tangent squared of theta plus 1 is equal to secant squared of theta. That's the second variation. And the third variation is 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. So all three of these can be established by, instead of writing A, B, and C, by writing opposite, adjacent, and hypotenuse, and then dividing by either opposite squared, hypotenuse squared, or adjacent squared, and just all these little tricks and tweaks. I'm not going to do the proof of going from the Pythagorean theorem to these three identities, but what I will show you is the basics of it, how we can actually take this first one and turn it into the second and third, because you must have these memorized. Asterisk, asterisk, asterisk. Second and third versions can be easily found from the first. So again, I'm going to tell you, I'm going to be completely honest about myself and the way I learn. I'm not great at just straight up memorization of facts. It's not my forte. I'm more about connecting dots, finding a logical flow, an A to a B to a C kind of deal. I can memorize some things, but then if I can find other things without just flat memorizing them, that's the way I like to do things. Do I tell you how to do things? No, I give you suggestions. So one student, Bob, maybe Bob memorizes these three outright, but then another student, Jane, only memorizes the first one, and she uses the trick I'm about to show you to get the second or the third when needed. Because once again, sine, cosine, and tangent are the ones that we see most often, the ones that we like to deal with most often because they're simpler, and it's just for consistency. Even more so, sine and cosine we can stick to most of the time. So this first version is going to be seen probably 5 to 10 more times frequently than the second and third versions. So that's why I memorize the first one, and then just under the rarer chances the second or third pop up, I can do this proof, if you will, I'm about to show you. So here's the basic idea. Start with the first, then divide all terms by either sine squared of the angle or cosine squared of the angle. It's kind of what I was saying that you can do with this to turn into the others. So start with the first one. By first, I mean sine squared plus cosine squared equals 1. This one's pretty easy to remember. And again, you'll see it over and over and over and over and over. These are a little more awkward with the mixing of tan and a secant or cotangent and a cosecant. At least these two have the cos together, at least these two don't. But it might be easy for you to put the cotangent on the wrong side or the secant on the wrong side. So let's start with the first one, sine squared theta plus cosine squared theta equals 1. So what I'm going to do is, and I said by either, not both, either, one or the other. Let's do the sine squared first. Is that going to end up giving us the second or the third one? I know, but you don't yet. Let's see which it is. So we're just going to divide all terms. Whatever we do to one side, do to the other. So we're not breaking any algebra rules. We're going to divide everything by cosine. I'm sorry, I said by sine squared, didn't I? So let's do the order I said. Divide all terms by sine squared. Now, why are we doing this? Because look what happens. We can cancel. Sine squared, this sine squared with this sine squared. Anything divided by itself is 1. So this is now just 1 here plus. Now, this middle term, cosine squared over sine squared. Let's go back and look at those tangent cotangent definitions, which were right here. Cotangent is cosine over sine, tangent is sine over cosine. So if we saw a relation of cosine over sine, we could instead write cotangent if we wanted. But what about those pesky squares? Well, it's the same thing on top of the same thing, both being squared. So that's just cotangent squared. So we're canceling and we're using trig identities. Trig identities, trig idents, that's what that says. Cosine over sine is cotangent. So if they're both being squared, it's cotangent squared. Equals 1 over sine squared. Well, 1 over sine we said was the reciprocal of cosecant. So instead of writing 1 over sine, if we don't want to write it as a fraction, we can instead write cosecant. But since it's sine squared, this is cosecant squared. So look at this. Just doing one simple algebraic step, we were able to get the third of the 3 identities. That was not anything super crazy complex, but you do have to remember how to establish it. So again, Jane, I said, would memorize this one and use this quick little algebra trick to find the other 2. If you're not Jane, if you're not going to remember this trick, you got to flat out memorize these 3 because that's the only trick I know off the top of my head to get to the second and third. Again, there are other ways. You can go straight from the a squared, b squared, and c squared to get to these, but it's the same exact concept as what we're doing here. It doesn't make it any easier. Okay, so how about if we again start with the sine squared plus cosine squared equals 1. I don't always say the angle out loud, but I do write it. And again, if you ever see those looking like 2's, they're not 2's, just poor handwriting from your teacher. This time, instead of dividing everything by sine squared, let's divide by, you guessed it, cosine squared of the angle. Not just the left side, not just the things that have trig functions. Whatever you do to the left, you got to do to the right. And then we cancel and use our trig identities. So this time the cosine squared plus cosine squared is going to cancel. So that's a +1. This right here is the +1. I'm skipping the first term just for a second. I brought down my equals. How about this sine squared over cosine squared? When we had cosine squared over sine squared, that was cotangent squared. If you remember from earlier, sine over cosine is tangent. With the being squared, that just makes this a tangent squared. And then equals 1 over cosine squared. Well, 1 over cosine, we said earlier, 1 over cosine was secant. So we can write that without a fraction. Well, if that's squared, that just makes this secant squared. And there we are. There's the second one, tan squared plus 1. Because when you were writing the second and third, you might have been wondering, why on this one did they write the 1 second, and then on this one did they write it first? Well, you don't have to because of the properties of addition. You can certainly write 1 plus tangent squared, or you could certainly write cotangent squared plus 1. The reason I write them in that order is because, now admittedly, I do have them memorized, but the memorization in my head is completely based on the tactic I just showed you. So in that tactic, it's very natural for the tangent squared to become the first term, and it's very natural for the cotangent squared to become the second term. So that's why in my head, the formulas are done this way. But you could certainly find a textbook where these 2 terms might be swapped, or these 2 terms might be swapped. But the secant squared has to be by itself, the cosecant squared has to be by itself in these forms. The first one especially, we'll see algebraic rearrangements of it constantly throughout the course. We're going to move the cosine squared over or move the sine squared over. So be prepared for that. So again, you have to memorize all 3 of these, or at least memorize 1 and be able to get the other 2 via a tactic that your teacher has taught you. And in my opinion, it's a simple tactic, but if you don't like it, memorize all 3. If you're only going to memorize 1, memorize the first, but you won't be making an A on the test. You might get a B. But if you don't memorize the first, you're probably looking at like a C. Because again, the first is used way more often, at least by design. All right, what do we got? 5 minutes. Let's go ahead and write the definition for cofunctions down. I don't think we'll get to examples, so don't want to waste time. Cofunctions. And I want to kind of point out that this is not the same as like sine versus cosecant. Those weren't cofunctions. It's just that cosecant has a co in front of the word secant to let you know it's the reciprocal of sine. Cofunctions work a little differently. This has to do with the fact that the two angles of a right triangle add to 90 degrees. The two, let me be more specific, non-right angles and I'll explain after I type these up. But the sine of theta is the same thing as doing the cosine of 90 degrees minus theta, or pi over 2 minus theta. The tangent of theta is the same thing as doing the cotangent of 90 degrees minus theta. And the secant of theta is the same thing as doing, you might be able to guess it, the cosecant of 90 degrees minus theta. Now these work the same way as reciprocal functions. You can write them out two different ways. I didn't do that for the reciprocals, but I will for these. So the other version is that the cosine of theta is equal to the, why did I start with the parentheses? Sine of 90 degrees minus theta. Notice the 90s come first. That is very important. The cotangent of an angle of theta is the tangent of 90 minus the angle, 90 degrees minus the angle, or pi over 2 minus the angle. And the cosecant of an angle is the same as the secant of 90 degrees minus the angle. That was a really ugly theta there. There we go. I gave you a couple quick definitions last class, and they were complementary and supplementary angles. The word complementary starts with CO, cofunctions. So these are complementary functions, complementary angles. Remember, complementary angles add to 90. It's like having two angles in a right triangle where we're not dealing with the right angle. So this works because this basic idea. I don't want blue, I want red. If this is a right triangle, if I call this angle, let's go with angle, I don't want to call them angle A and B. Let's just call this one theta, just to keep it appropriate. Let's pretend this angle for a second was 1 degree though. If this was 1 degree, so this is an if game, if this was 1, this would have to be 89 in degrees. I'm just skipping right at the writing the symbol, because they have to add to 90. If this was 2, this would have to be 88 so that they add to 90. If this was 10 degrees, this would have to be 80 degrees so that they add to 90. But I don't just have to pull that 80 out of my head. I can say that this angle right here is 90 minus 10, which is 80. That's the relationship between the two non-right angles of a right triangle. If you know one of them, you can find the other by doing 90 minus the first. So if the first angle is theta, the second angle has to be 90 degrees. I drew that triangle too small. There we go. If this is theta, this has to be 90. I'm still doing that as a bad setup. 90 degrees minus theta. That's that angle. I could swap them. If I call this angle theta, then that makes this one 90 degrees minus theta. Now you might understand so far, but then why does this work? Well, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. When you change the angle, opposites and adjacents change. So the opposite of theta, this is the opposite of 90 minus theta, but the opposite of theta is also the adjacent of 90 degrees minus theta. So the sine of one is the cosine of the other. You just changed the concept of opposites and adjacents. So the opposite of 90 minus theta would be the adjacent of theta. So this is going to give us a strength if maybe the math or the information we're given is up here, but we'd rather perceive it from here. So if we know this angle is, say, 42 degrees, we can just say, hey, let's deal with the 47-degree angle instead, because I'd rather deal with its sine instead of the cosine of this one up here. So that's the strength. That does not conclude 7.2.
Classic, meant to say 5.2 there. We're just going to do a couple quick examples using this stuff real quick. Just got to switch. Give me a second. All right, so when I had started this video, I was having a bit of a glitch with my Word program and everything. So you won't get to see me actually type out the example 3 and writing A and B. So I'm just going to leave this on the screen for a minute so you can catch up. But for example 3, and again, this will be our last examples for the day, just a couple quick ones. Find a cofunction with an identical value. Now, again, I'm not asking what is the value. I'm just saying if I ask you for the sine of 1 degrees, it would be like the cosine of 89 degrees. They would be the shared value based on the previous formulas. So again, we're not going to actually say the sine of 26 degrees is 0.3, 0.4, something like that. It doesn't matter. It's not the point. We're just trying to turn this into an equivalent cofunction. That's all we're doing. So A is sine of 26 degrees, and then B, when we get to it, will be the cotangent of 81 degrees. All right.
So reinventing the wheel. Thank you for getting my attention. I don't know why the chat wasn't popping up on my screen. It usually does. All right, so the sine of 26 degrees. We said the cofunction of sine is cosine. This just puts us on the opposite angle in a right triangle. So this would be the cosine of 90 degrees minus 26 degrees. We said 90 minus 26 is going to be 64. So that would be the equivalent of cosine of 64 degrees. And I said, we're not going to figure out this yet. We'll do some of that in the next example, though. Spoilers, with a calculator. Then the cotangent of 81 degrees. Its cofunction is tangent. So the cotangent of this angle would be the tangent of this angle. So let's switch that to tangent, but we have to do 90 degrees minus 81 degrees, which is 9 degrees. So the cotangent of 81 degrees is the tangent of 90 degrees. And we will actually show these in a calculator that they are the same after the example. Third and last example of this, let's do the secant of pi over 6. I'm really glad y'all got me before this one, because this one's in radians. So secant and cosecant are cofunctions. So the secant of one angle is the cosecant of another. Remember, these are not reciprocal relations. These are going to a different angle relations. So this would be cosecant of, and I don't want to do 90 degrees minus pi over 6 since that's in radians. Now, one option is you could convert your pi over 6 to degrees, which spoilers would be 30 degrees. 90 minus 30 is 60. But if you write cosecant of 60 degrees in Mymathlab, it's probably going to mark it wrong. If the original problem's in radians, it probably wants the answer in radians. So I verbally went over how to convert everything. Well, not how to convert, you multiply by 180 degrees over pi, and that's how you get your 30 degrees. But let's actually do the radian math. So 90 degrees is pi over 2. 180 degrees is pi, so 90 is pi over 2, minus the original argument of pi over 6. So to the side, you got to do pi over 2 minus pi over 6. You got to get an LCD between a half and a sixth, basically. So pi over 2 minus pi over 6. The LCD between 2 and 6 is 6. So we're going to change those denominators to 6s. For the first one, 2 will go into 6 3 times. 3 times pi is 3 pi. For the second one, 6 goes into 6 once. 1 times pi is pi. 3 pi minus 1 pi is 2 pi. Remember, there's an implied 1 here that we normally don't write. You're free to in your work, but I don't like keeping it there because it's bad for answers. So pi over 2 turned into 3 pi over 6. If you're rusty with LCDs, I've already told you, you can't be rusty. You've got to de-rust. But then 2 and 6 will reduce to a 1 and a 3. Those are kind of ugly, 2s and 6s. 2 pi over 6. 2 and 6 reduce to a 1 and a 3. So that becomes pi over 3. So this subtraction is pi over 3. So the answer would be cosecant of pi over 3. Now, pi over 3 is actually 60 degrees, and that's one of the angles that we will be discussing on how to convert them. Not this moment. I said convert, I meant actually simplify. So let's pull out a calculator because we're going to need it for the next set of problems. Get my TI-83. If you have better than a TI-83, that is perfectly fine. This is kind of the bare minimum. I mean, a TI-82 will do the job, but I don't even know where you uncovered that relic of the past if you got a TI-82. There's my digital TI-83. Now remember, this is important moving forward in our class. You have to check your mode. There's a radian mode and a degree mode, because when you type these things in, so like the cosine of 64 degrees, here's my cosine button. If I do 64 and then close the parentheses, right now I get 0.3918, but if I change the mode, if I go down and make it degrees, so it was actually in radians originally, which means it was wrong. Then hit second quit to get out of that screen. So because 64 is degrees, this was calculated in radians. This is wrong, 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 wrong. Cosine of, oops, cosine of 64 degrees. You don't have to close the parentheses for a singular argument like this, but we'll get into more complicated problems, so it's a good habit. Look at that, it's a different answer. It's 0.438, blah, 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 blah. So your answer will be dependent on the mode. If you're in degree mode, you'll get one answer. If you're in radian mode, you'll get another answer. So 64, that was a degrees, so I got to make sure I'm in degrees. I got to make sure, oh, the second answer was right. So let me just display the correct one. This is in degrees, 64 degrees, boom, there's the answer. How about the tangent of 9? We can hit tangent, 9. We're still in degrees. It doesn't just reset automatically. I'll check to be safe. Yep, it said degrees. And it's 0.158, blah, 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 blah. So this is the ratio of the opposite to adjacent for the tangent or the adjacent to the hypotenuse for the cosine. You don't have the actual links, but that's what they would be if you divided them out. That can be just as helpful. Whether this is a big number or a small number can be helpful. How about cosecant? I see sine, cosine, and tangent, but I don't see secant, cosecant, and cotangent up here. That's because they're not in any TI-83 or TI-84. They might be in a more advanced graphing calculator, but I'm going to assume this is what we're all working with. Cosecants are reciprocals of sines. So if I want to do the cosecant of pi over 3, here's what I do. And it's not this. You see in yellow sine raised to the -1, that looks like a reciprocal. It's actually not. That's called an inverse sine function. It is different. We will study it. So please note those yellow ones on my keyboard. It doesn't sound like quite the right term. On the calculator, kind of above the buttons, those are inverse trig functions. The way to do a cosecant, because it's the reciprocal of sine, you do 1 divided by sine. Now that says pi over 3. So to get pi, I gotta get this yellow one, so second, and then caret, divided by 3, close the parentheses, and I'm gonna hit enter, and then I'm gonna say, do you think this is right or wrong? 54.7, blah, 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 blah. Now, just looking at the number, you don't know any sense of what these should be, so that's not gonna help you. What I mean by is it right or wrong is, were you in the correct mode? So pi is a radian, but our mode's in degrees, so that's not right. So to get that final one correct, I actually got to switch back to radian mode. And I can actually use second and enter to recall the last thing I typed. It's a shortcut, so I don't have to type the whole thing again. And you can see that the answer is actually 1.15, a significantly smaller value. So those are subtle nuances that you have to pay attention to. You have to be careful with. So let's do that for example 4. We are going to evaluate in a calculator. We're going to have the sine of 26 degrees. I'll go ahead and write them all up at once since it's just type it.
Sorry about that. I was sitting there counting how much time we had, but I did say I was going to make the cofunctions the last example, so I'll stick to it. So when we come back next time, we're just going to do a couple of quick typing things in calculators. However, I'm going to go ahead and say that this section is complete. So again, I'm going to say that 5.2 has been completed. You just didn't see 2 quick examples, which is once again, literally just typing things in a calculator. So hopefully that won't be a problem. And you'll be able to see that first thing when we come to class on the 1st. So the 1 or 2 homework problems on it, you would have plenty of time to do that over the 2 days between that and the 3rd if you absolutely had to see me do it first. Just know that you'll have to check your mode. There's a radians and a degrees mode. If you've got a calculator you don't know how to use, Google would be your friend there, but that'll make the difference because degrees and radians operate differently in trig. So we'll call it a day there. Have a great weekend. Have a great holiday. Please email me if you have any questions. Remember, if you are one of my 2 or 3 new students, that you need to enroll in my math lab today by 5 p.m. I don't want to have to delete you. I want you to be able to stay in the class. I cannot actually legally answer where I got my digital calculator because I don't know what the repercussions of it would be. But if you Google, free TI-83 calculator, something like that, or TI-83 ROM, I'm pretty sure the internet can help you without getting me in trouble, because that's very awesome and it'll save you what, like $80 for one of those things new, and everything's got hyperinflation after the pandemic, so maybe they're even more than that. I don't know. All right, so on that fun note, have a good weekend. Take care. Once again, email me if you have any questions, and get in my math lab if you haven't already. Cheers.